हेलो दोस्तों, वेलकम टू द साइनिंग ब्रेन। आज हम एनसीईआरटी साइंस का चैप्टर नंबर 3 मोशन एंड टाइम को पढ़ने जा रहे हैं। चलिए स्टार्ट करते हैं। इन क्लास 6 यू लर्नड अबाउट डिफरेंट टाइप ऑफ मोशंस। यू लर्न दैट अ मोशन कुड बी along a straight line. It could be circular or periodic. Can you recall these three type of motions? This table 13.1 gives some common example of motions. Identify the type of motions in each case. Here table 13.1 sub example of different type of motions. It is common experience that the motion of some object is slow while that of other is fast. 13.1 Slow or fast. We know that some vehicles move faster than others. Even the same vehicle may move faster or slower at different times. Make a list of 10 objects moving along a straight path. Group the motion of this object as slow as fast. How did you decide which object is moving slow and which one is moving fast? If the vehicles are moving on a road in the same direction, we can easily tell which one of them is moving faster than the other. Let us look at the motion of the vehicles moving on a road. Activity 13.1. Look at figure 13.1. It shows the position of the some vehicle moving on a road in the same direction at some instant of time. Now look at figure 13.2. It shows the position of the same vehicle after some time. From your observation of two figures, answer the following question. Which vehicle is moving the fastest of all? Which one of them is moving the slowest of all? The distance moved by the object in a given interval of time can help us to decide which one is faster or slower. For example, imagine that you have gone to see off your friend at the bus stand. Suppose you will start paddling your bicycle at the same time as the bus begin to move. The distance covered by you after 5 minutes would be much smaller than that covered by the bus. Would you say that the bus is moving faster than the bicycle? Here figure 13.1, you can see the vehicle moving in the same direction on a road. 13.2 figure, position of vehicle shown in figure 13.1 after some time. We often say that the faster vehicle has a higher speed. In a 100-meter race, it is easy to decide whose speed is the highest. One who takes shortest time to cover the distance of 100 meter has the highest speed. 13.2 Speed. You are probably familiar with the word speed. In the examples given above, a higher speed seems to indicate that a given distance has been covered in a shorter time or a larger distance covered in a given time. The most convenient way to find out which of the two or more object is moving faster is to compare the distance moved by them in a unit time. Thus, if we know the distance covered by two buses in 1 hour, we can tell which one is faster. We call the distance covered by an object in a unit time as the speed of the object. When we say that a car is moving with a speed of 50 km per hour, it implies that it will cover a distance of 50 km in 1 hour. However, a car seldom moves with a constant speed for 1 hour. In fact, it starts moving slowly and then pick up the speed. So, when we say that the car has a speed of 50 km per hour, we usually consider only the total distance covered by it in 1 hour. We do not bother whether the car has been moving with a constant speed or not during that hour. The speed calculated here is actually the average speed of the car. In this book, we shall use the term speed for average speed. So, for us, the speed is the total distance covered divided by the total time taken. Thus, speed equal to total distance covered divided by total time taken. In everyday life, we seldom find objects moving with a constant speed over long distances or for long duration of time. If the speed of an object moving along a straight line keeps changing, its motion is said to be non-uniform. On the other hand, an object moving along a straight line with a constant speed is said to be uniform motion. In this case, the average speed is the same as the actual speed. We can determine the speed of given object once we can measure the time taken by it to cover a certain distance. In class 6 you learned how to measure distance, but how do we measure time? Let us find out. 13.3 Measurement of time. If you did not have a clock, how would you decide what time of the day it is? Have you ever wondered how our elders could tell the approximate time of the day by just looking at shadow? How do we measure time interval of a month, a year? Our ancestors noticed that many events in nature repeats themselves after definite interval of time. For example, they found that the sun rises every day in the morning. The time between one sunrise and the next was called a day. Similarly, a month was measured from one new moon to the next. A year was fixed as the time taken by the earth to complete one revolution of the sun. Often, we need to measure intervals of time which are much shorter than a day. Clock or watches are perhaps the most common time measuring devices. Have you ever wondered how clock and watches measure time? The working of clock is rather complex, but all of them make use of some periodic motion. One of the most well-known periodic motion is that a simple pendulum. 13.3 Figure some common clock. A. Wall clock. B. Table clock. C. Digital clock. Figure 13.4 a simple pendulum, and 13.4b different position of the bob of an oscillating simple pendulum. A simple pendulum consists of a small metallic ball or a piece of stone suspended from a rigid stand by a thread. The metallic ball is called a bob of the pendulum. Figure 13.4a shows the pendulum at the rest in its mean position. When the bob of the pendulum is released after taking it slightly to one side, it begins to move to and fro. Figure 13.4b. The to and fro motion of a simple pendulum is an example of periodic or an oscillatory motion. The pendulum is said to have complete one revolution when its bob started from its mean position O, moves to A, to B, and back to O. The pendulum also completes one oscillation when its bob moves from one extreme position A to one extreme position B and come back to A. The time taken by the pendulum to complete one oscillation is called its time period. Activity 13.2. Set up a simple pendulum as shown in figure 13.4a with thread or a string of length nearly 1 meter. Switch off any fan nearby. Let the bob of the pendulum come to rest at its mean position. Mark the mean position of the bob on the ground below it or on the wall behind it. To measure the time period of the simple pendulum, we will need a stopwatch. However, if a stopwatch is not available, a table clock or wrist watch can be used. To set the pendulum in motion, gently hold the bob and move it slightly to one side. Make sure that the string attached to the bob is taut while you displace it. Now, release the bob from its displaced position. Remember that the bob is not to be pushed when it is to be released. Note the time on the clock when the bob is at the its mean position. Instead of the mean position, you may note the time when the bob is at one of its extreme position. Measure the time the pendulum takes to complete 20 oscillations. Record your observation. In table 13.2, the first observation shown is just a sample. Your observation could be different from this. Repeat this activity a few times and record your observation. By dividing the time taken by 20 oscillation by 20, get the time taken for one oscillation for the time period of the pendulum. Is the time period of your pendulum nearly the same in all cases? Note that a slight changes in the initial displacement does not affect the time period of your pendulum. Nowadays, most clock or watch have an electric circuit with one or more cells. These clocks are called quartz clock. The time measured by quartz clock is much more accurate than that by the clock available earlier. Here table 13.2 is given. Time period of a simple pendulum. Length of the string is 100 centimeter. Some information is there. There is an interesting story about the discovery that the time period of a given pendulum is constant. You might have heard the name of famous scientist Galileo Galilei, AD 1564 to 1642. It is said that once Galileo was sitting in a church, he noticed that a lamp suspended from the ceiling with a chain was moving slowly from one side to other. He was surprised to find that his pulse beat the same number of times during the interval in which the lamp completed one oscillation. Galileo experimented with various pendulums to verify his observation. He found that a pendulum of given length takes always the same time to complete one revolution. This observation led to the development of the pendulum clock. Winding clock and wristwatch were refinement of the pendulum clock. Unit of time and speed. The basic unit of time is a second. Its symbol is S. Larger unit of time are minute and hours. You already know how these units are related to one another. What would be the basic unit for the speed? Since the speed is distance per time, the basic unit of speed is meter per second. Of course, it could be expressed in other unit such as meter per minute or kilometer per hour. You must remember that the symbol of all units are written in singular. For example, we write 50 kilometer and not 50 kilometers, or 8 centimeter and not 8 centimeters. Bojo is wondering how many seconds there are in a day and how many hours in a year. Can you help him? Different unit of time are used depending on the need. For example, it is convenient to express your age in years rather than days or hours. Similarly, it will not be wise to express in years the time taken by you to cover the distance between your home and your schools. How small or large is a time interval of 1 second? The time taken in saying around 2001 is nearby 1 second. The time taken in saying aloud 2001 is nearby 1 second. Verify it by counting aloud from 2001 or 2010. The pulse of the normally healthy adult at the rest beat about 72 times in a minute, that is about 12 times in 10 seconds. This rate may be slightly higher for children. Paheli wonders how time was measured when pendulum clock were not available. Here the information is: the smallest time interval that can be measured with commonly available clock and watch is 1 second. However, now special clocks are available that can be measured time interval smaller than a second. Some of these clocks can measure time interval as small as millionth or even 1 billionth of the second. You might have heard the term like microsecond and nanosecond. 1 microsecond is 1 millionth of second. A nanosecond is 1 billionth of a nanosecond. Clock that measures such a small time interval are used for scientific research. The time measuring device used in sports can measure time interval that are 1/10 or 100 of a second. On the Other hand, time of the historical events are started in terms of centuries or millenniums. The age of stars and planets are often expressed in billions of years. Can you imagine the range of time interval that we have to deal with? Many times, measuring devices were used in different parts of our world before the pendulum clock became popular. Sundial, water clocks, and sand clocks are some examples of such devices. Different design of these devices were developed in different part of the world. Figure 13.5. Measuring speed. Having learned how to measure time and distance, you can calculate the speed of an object. Let us find the speed of a ball moving along the ground. Activity 13.3. Draw a straight line on the ground with chalk powder or lime and ask one of your friends to stand 1 to 2 meters away from it. Let your friend gently roll a ball along the ground in a direction perpendicular to the line. Note that the time at the moment the ball crosses the line and also when it comes to rest. How much time does the ball take to complete to rest? Figure 13.5. Some ancient time measuring device. A. Sundial at Jantar Mantar, Delhi. B. Sand clock. C. Water clock. Figure 13.6. Measuring the speed of a ball. Measure at a distance between the point at which the ball crosses the line and the point where it comes to rest. You can use a scale or a measuring tape. Let different group repeat the activity. Record the measurement in table 13.3. In each case, calculate the speed of ball. You may now like to compare your speed of walking or cycling with that of your friend. You need to know the distance of the school from your home or from some other points. Each one of you can then measure the time taken to cover that distance and calculate your speed. It may be interesting to know who amongst you is the fastest. Speed of some living organisms are given in table 13.4 in kilometer per hour. You can calculate the speed in meter per second yourself. Rocket launching satellite into Earth orbits often attains speeds up to 8 km per second. On the other hand, a tortoise can move only with a speed of 8 cm per second. Can you calculate how fast is the rocket compared with the tortoise? Once you know the speed of the object, you can find the distance moved by it in a given time. All you have to do is to multiply the speed by time. Thus, distance covered equal to speed into time. You can also find the time an object would take to cover a distance while moving with a given speed. Time taken equal to distance by speed. Bojo wants to know whether there is any device that measures the speed. You might have seen a meter fitted on the top of the scooter or a motorcycle. Similarly, meter can be seen on the dashboard of the car, buses and other vehicles. Figure 13.7 shows the dashboard of the car. Note that one of the meter has kilometer per hour written at one corner. This is called a speedometer. It records the speed directly in kilometer per hour. There is also another meter that measures the distance moved by the vehicles. This meter is known as an odometer. Figure 13.7 dashboard of the car. While going for a school picnic, Paheli decided to note the reading on the odometer of the bus after every 30 minutes till the end of the journey. Later on, she recorded her reading in table 13.5. Can you tell how far was the picnic spot from the school? Can you calculate the speed of the bus? Looking at the table, Bojo asks Paheli whether she tells how far they would have traveled till 9:45 a.m. Paheli had no answer to this question. They went to their teacher. She told them that one way to solve this problem is to plot a distance time graph. Let us find how such a graph is plotted. Figure 13.8, a bar graph showing runs scored by a team in each over. Distance time graph. You might have seen that newspaper, magazine, etc. present some information in various form of graph to make it interesting. The type of graph shown in figure 13.8 is known as a bar graph. Another type of graphical representation is a pie chart. Figure 13.9. The graph shown in figure 13.10 is an example of line graph. The distance time graph is a line graph. Let us learn to make such a graph. Figure 13.9, a pie chart showing composition of air. Figure 13.10, a line graph showing change in weight of a man with age. Take a sheet of graph paper, draw two lines perpendicular to each other on it as shown in figure 13.11. Mark the horizontal line at x o x dash. It is shown as the x-axis. Similarly, mark the vertical line y o y dash. It's called the y-axis. The point of intersection of x o x and y o y dash is known as the origin. The two quantities between which the graph is drawn as shown along these two axes. We show the positive value on the x-axis along OX. Similarly, positive value of y-axis are shown along OY. In this chapter, we shall consider only the positive value of quantities. Figure 13.11, x-axis and y-axis on a graph paper. Therefore, we shall use only the shaded part of the graph shown in figure 13.11. Bozo and Paheli found out the distance traveled by the car and the time taken by it to cover that distance. Their data is shown in figure table 13.6. Table 13.6, the motion of a car. You can make the graph by following the steps given below. Draw two perpendicular lines to represent the two axes and land them and mark them as OX and OY as figure 13.11. Decide the quantities to be shown along the x-axis and that to be shown along y-axis. In this case, we show the time along the x-axis and the distance along the y-axis. The time in x-axis and distance in y-axis. Choose a scale to represent the distance and another to represent the time on the graph. For the motion of the car, scales could be time 1 minute equal to 1 centimeter, distance 1 kilometer equal to 1 centimeter. Mark values for the time and the distance on the respective axes according to the scales you have chosen. For the motion of the car, mark the time 1 minute, 2 minutes, dash 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 on the x-axis from the origin O. Similarly, mark the distance 1 kilometer, 2 kilometer, dash 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 on y-axis. Figure 13.12. Now you have to mark the points on the graph paper to represent each set of the value for distance and time. Observation record at serial number 1 in table 13.6 shows that at time 0 minute the distance moved is also 0. The point corresponding to this set of values on the graph will therefore be origin itself. After 1 minute, the car has moved a distance of 1 kilometer. To mark this set of value, look for the point that represent 1 minute on the axis. Draw the line parallel to the y-axis at this point. Then draw a line parallel to the x-axis from the corresponding points. to distance 1 kilometer on y-axis. The point where these two lines intersect represents this set of values on the graph, figure 13.12. Similarly, mark on the graph paper the point corresponding to the different set of values. At figure 13.12, making a graph. Here you can see in x-axis time in minute and y-axis distance in kilometer, where 1 minute is equal to 1 kilometer and 2 minutes is equal to 2 kilometer. You can make a simple parallel line and connect it. Figure 13.3, making a graph. Figure 13.12 shows the set of points on the graph corresponding to position of the car at various times. Join all the points on a graph as shown in figure 13.13. It is a straight line. This is the distance time graph for the motion of the car. The distance time graph is a straight line. If the distance time graph is a straight line, it indicates that the object is moving with a constant speed. However, if the speed of the object keeps changing, the graph can be of any other shape. Figure 13.14, distance time graph of the bus. Generally, the choice of the scale is not as simple as in the example given in figure 13.12 and 13.13. We may have to choose two different scales to represent the desired quantity on the x-axis and the y-axis. Let us try to understand this process with an example. Let us again consider the motion of the bus that looks Paheli and her friends to the picnic. The distance covered and the time taken by the bus are shown in figure table 13.5. The total distance covered by the bus is 80 km. If we decide to choose a scale of 1 km equal to 1 cm, we shall have to draw an axis of length 80 cm. This is not possible on a sheet of paper. On the other hand, a scale of 10 km equal to 1 cm would require an axis of length only 8 cm. This scale is quite convenient. However, the graph may cover only a small part of the graph paper. Some of the points to be kept in mind while choosing the most suitable scale for drawing a graph paper are the difference between the highest and the lowest value of each quantity, the intermediate value of each quantity, so that with the scale chosen it is convenient to mark the value on the graph and to utilize the maximum part of the paper on which the graph is to be drawn. Suppose that you are given a graph paper of size 25 cm into 25 cm, one of the scale which meets the above condition and can accommodate the data of table 13.5 could be distance equal to 5 cm equal to 1 cm, distance equal to 5 km equal to 1 cm, and time 6 minutes equal to 1 cm. Can you now draw the distance time graph for the motion of the bus? Is the graph drawn by you similar to that figure 13.13? Distance time graph provide a variety of information about the motion when compared to the data presented by a table. For example, table 13.5 give information about the distance moved by the bus only at some definite time interval. On the other hand, from the distance time graph, we can find the distance moved by the bus at any instant of time. Suppose we want to know how much distance the bus had traveled at 8:15 am. We mark the point corresponding to the time 8:15 am on the x-axis, figure 13.14. Suppose this point is A. Next, we draw a line perpendicular to the x-axis or parallel to the y-axis at a point A. We then mark the point T on the graph at which figure perpendicular line intersects it, figure 13.14. Next, we draw a line through the point T parallel to the x-axis. This intersects the y-axis at point P. The distance corresponding to the point B on the y-axis, OB, gives the distance in kilometer covered by the bus at 8:15 am. How much it how much is this distance in kilometer? Can you help Paheli to find the distance moved by the bus at 9:45 am? Can you also find the speed of the bus from its distance time graph? Now keywords: bar graph, oscillation, time period graph, simple pendulum, uniform motion, non-uniform motion, speed and unit of time. Here in this figure 13.14 you can see the distance time graph of the bus. Here time in am, here the time is shown in am: 8 to 8:30, 9, 9:30, 10, and distance in kilometer: 0, 10, 20, 30, 40, 50, 60, 70, 80, 90. So this is the end of this chapter. Okay friends, अगले वीडियो में हम नेक्स्ट चैप्टर के बारे में पढ़ेंगे. तब तक के लिए थैंक यू.